Okay, so I just want to complete the discussion of the hydrogen atom, or just electrons and atoms in general. And we'll move on to perturbation theory next week. Oh, and also the Wigner classification. Okay. Any questions before we start? Okay. So let's see. Right. Okay, so there's a couple of things that I need to explain. So the first one has to do with bosons versus fermions, and the so-called Pauli exclusion principle. Same idea as the spin statistics theorem. And the second thing is perturbations, or really absorption and emission. Selection rules. I tried to explain last time, but I didn't make it, so I'll fix it this time. And then we'll look at kind of multiple electrons and degeneracies. Okay, now this spin statistics thing is not something that we have time to completely prove. I mean, I'm just going to state it and explain how it works, but to prove it would require a lot more machinery. Usually you prove it in a first class on quantum field theory. So it's all about having multiple, it's all about indistinguishable particles. Okay, so let me explain. So if we go way back to the beginning of the course, where we talked about the axioms of quantum mechanics, one of the fundamental aspects of quantum mechanics is that when you combine two systems, you have to take the tensor product of their state spaces, of their quantum Hilbert spaces. So if two particles, so a joint system consisting of two particles, doesn't really have to be particles, two particles or systems. let's call them say V1 and V2 vector spaces. Has state space V1 tensor V2. No surprise there. This is from axioms. Okay. Now, one of the phenomena of elementary particles, which is a great blessing, is that a lot of them are pretty much exactly the same. There's untold numbers of electrons in the universe, and they're all the same. There has never been two electrons that are somehow different. Because if that were the case, then we would have called them differently. Like, for example, muon. Muon is basically an electron, but it doesn't behave like an electron, so we call it something else. But the point is that the vast majority of electrons are all exactly the same, and so exactly, in fact, that they're completely indistinguishable when they're together. So, well, okay, you can puzzle about this philosophically, but if I tell you that I have two electrons in a box, they are really indistinguishable in the following sense, that if you kind of blindfold yourself and God switches the particles, then there is no way to tell. The same physical state occurs. So in other words, yeah, if you have a multi-electron system or a multi-proton system or any kind of elementary particle of the same type system, then and if you do not separate them by some other external observable, like, for example, you might be in a situation where you put one electron here and one electron there, and so yeah, sorry, let me not make this more complicated than it needs to be. So the point is that these particles are indistinguishable. If you switch them, you should have the same physical state. That means that the electrons do not have some internal, they don't have secretly a label on them that says, I'm the first electron and I'm the second one. They don't have that property. They don't have an individuality in any way. If you are going to label one of them as electron 1 and the other electron 2, that's your choice. It's an additional structure that is not present in the system. Okay. Yeah. Question.
So just to be clear, like when you say indistinguishable, like it's indistinguishable, like the composite state is indistinguishable from the other state before you swap.
What other state? What other state?
Like if you have two electrons in some state, you swap them, the new state will be the same up to a phase, right? There's still could be a phase change in the state.
So I don't like it when people who kind of know the answer to the development try to interrupt and give the answer before the answer is given. You know what I mean? Like, it's like spoiling a movie. It's like recommending to someone, why don't you watch this movie where all of the main characters die?
I mean, I don't think that's the same thing.
I think it is.
Well, all right, that's fair enough. Yeah.
I haven't gotten yet to phases and so on. I'm trying to illustrate first the fact that from a physical point of view, from a philosophical point of view, okay, that's why I started up high up first before getting into complex numbers, right? That there is no intrinsic meaning even to the activity of swapping the electrons. Okay, it does not, when you have two electrons in a box, right? You cannot even define what it means to swap them, because you would need to know which is the first electron, which is the second electron, and let me change their positions. Okay, so I'm trying to illustrate that there's something deeper, that they don't have an individual ordering at all. Okay, so so that means that if we have two identical particles, okay, it's incorrect to say that their state is in V tensor V. This is not the combined state space. Okay, because this makes it seem as if you can distinguish, for example, between this and this. These would be two different states in the tensor product. And these states, you would interpret them as saying that the first electron is spin up and the second is spin down, in this case. Whereas in this case, the first electron is spin down and the second is spin up. But this is impossible in reality because you don't know which is the first electron. There is no way at all of indicating one electron versus the other. It's like trying to, it's like, you know, maybe when parents have, you know, twins, identical twins, maybe they should not name them. You know, maybe they should have one name. And, you know, there should, you know, if they were truly identical, it should not be possible to remember which one has which name, because they're identical. They cannot be distinguished individually. Sorry, probably to half of the class, I probably sound insane. But the reason is it's kind of difficult to articulate what identical particles means. What identical particles means is really this. It's a change of the axioms in a way. It's saying that when you take a composite system of electrons, it is incorrect to put them, you know, unless there's some other way that you can reliably distinguish them, unless you have a way of labeling them, you know, using external apparatus or something, which is, here we're only considering the internal states, that it's incorrect to say that their joint state is in V tensor V. So what's going on here? What's going on is that there's an ambiguity in the description. So describing a pair of identical particles as states in V tensor V is not quite right. There is an ambiguity in the description. The description is using information that we don't actually have, that doesn't actually exist. So one way of dealing with this is to try to restore the ambiguity that truly does exist in physics. So to restore the ambiguity, sorry, I phrased this wrong. There is a precision in the description which does not exist. Not necessarily exist. In other words, we should not physically be able to distinguish A tensor B from B tensor A. Okay, so we must restore the vagueness or the ambiguity by considering an action of a very simple group, the swapping group, which is otherwise known as Z2, or the group with just plus or minus 1 elements. This group acts on V tensor V. And you could say that 1 acts on U tensor V by doing nothing, and minus 1 acts on U tensor V by switching. It's better if I don't use plus or minus 1, because then it'll get confused with plus or minus 1 in the complex numbers, which acts on V tensor V. So it's better if I just say that this is just a group generated by sigma, such that sigma squared is equal to 1. And sigma acts, the switching map acts on a state U tensor V to give V tensor U. Okay, so this means that this is a representation of the group Z2. So representation of Z mod 2Z. Is that okay so far? So this switching map is what we're going to use, because we want to implement the idea that when you switch two identical particles, the state should not change. And so switching, right, is really an operation on a fictitious Hilbert space where you could distinguish the particles. And so if we could distinguish the particles, we would have V tensor V, and then we could kind of restore the ambiguity between the two states by somehow considering this switching action. Okay, and and then we look for subspaces of states in V tensor V, which are unchanged by sigma. Okay, these will be the identical twin states. So identical particle states are not states in V tensor V, but rather they're subspaces of V tensor V, which are not affected by the switching map. Is that concept clear? Let me take a question on it.
Could we think of these as the symmetric tensors? Or is that not a useful way to think of it?
Okay, so well, let's see. So so what are these subspaces? That's what you're asking. You're asking the next. You want to know what's coming up in the movie. You're like those people who talk in the movie, who are like, like, what's going to happen next? But yes, okay, fair enough. I shouldn't kind of insult my audience. Okay, so so what are these subspaces? Okay, so you definitely put your finger on one of them. So if you consider U tensor V, that's not a twin state, because it's not invariant. Let's say U and V are not the same vector. It's not, it would be sent by the switching map to V tensor U. So these are, in principle, in general, these are different states. So these are definitely changed. They're affected by the switching. But if I what they call average over the group, if we average over the group action, that means that we should take the element, and then we should add what happens when you affect this by sigma. So, and this will be U tensor V plus V tensor U. Now we have something that actually is left alone by the switching map. So now sigma of U tensor V plus V tensor U is equal to U tensor V plus V tensor U. So this is a permitted twin state. It's genuinely the same upon switching. And so switching, in a way, is not really an operation. So we've removed the kind of fictitious specificity of the state in V tensor V. And these states, states are called the symmetric tensors. So S2V is a subspace of V tensor V. And this consists of the states invariant under sigma. So what is sigma? Sigma is a map from V tensor V to itself. It's a linear map. Okay, and it squares to 1. So that means sigma squared minus 1 is equal to 0, and it means that sigma minus 1, sigma plus 1 is equal to 0. So we see that the eigenvalues, the possible eigenvalues, are plus and minus 1. And this is the plus 1 eigenspace. S2V is the plus one eigenspace of sigma. But sigma has another eigenspace. So what about the minus 1 eigenspace? So if we take the U tensor V minus V tensor U, instead of the sum, then we see that sigma applied to this is going to be V tensor U minus U tensor V, which is minus psi. So we have sigma of psi is minus psi. So it's in the -1 eigenspace. And so these are called skew symmetric tensors. Wedge 2V is also a subspace of V tensor V, consisting of skew symmetric tensors, which is the -1 eigenspace. So we basically have these two eigenspaces, and it's a obvious fact that V tensor V actually breaks up exactly as a sum of these two subspaces. Okay, so why am I talking about the -1 eigenspace? Well, this is exactly what Christopher was saying, that if I have a state in Hilbert space, and if I compare it to a scalar multiple of it, those two are different vectors, but they have the same line. They generate the same line. So they generate the same physical state. This state and this state are actually the same state, the same physical state. So this condition is equally good from the point of view of physical indistinguishability as this one. If sigma psi is equal to psi, or if sigma psi is equal to minus psi, they both qualify as being a twin state. You see what I'm saying? Either one of these subspaces are physically unaffected by sigma, because they're only affected by a phase. In particular, it's plus or minus 1 in this case. So we have a problem. We have a problem, which is, okay, so which one is it? Okay, should I think of my indistinguishable pair, my twin state, should I think of it as a tensor in here, or a vector in here, or a vector in here? These are the two possibilities. And so, basically both occur. And when this one occurs, so if a particle or system V behaves if a particle system V, when there are multiple identical copies has states in wedge 2V, we call these fermions. When it's in S2V, we call these bosons. So this is what physicists mean when they talk about statistics. Statistics is about many things. I mean, statistics is the study of many things happening, like multiple things happening, right? A large number of people together, they are subject to statistics. So 2 is a large number. There's 2 particles. Therefore, they have some kind of statistics. They have some kind of behavior when there's more than one. Okay, that's what the statistics means. Okay, the question is, what kind of statistics do the particles have? How do they behave when they're in large numbers? If they are in this type of tensor product, then they're called bosons, and if they're in this one, they're called fermions. Is that clear? Any questions about this? It doesn't have to be a particle as well, right? You could imagine that you could have 2 twin people, or even molecules, let's say, which are presumably exactly the same, like maybe in an identical state somehow. And there would be a question as to, how they behave under switching. Should they mathematically be treated as an element of the second symmetric power, or in the second wedge power, the skew symmetric power? And this is just a question of like the mathematical model, right? As I said, so far we have no way of determining which one is which. There's 2 possibilities, and there's 2 types of particles. There's 2 types of elementary quantum systems. That's what I'm saying: bosons and fermions.
I'm a bit confused. Can I ask a quick question?
Yeah.
So if I take a particle or a state in V, when you say identical copy, that means I tensor it with itself, but then isn't it necessarily symmetric?
No, I don't mean that the state is identical. Like, of course, if you have a state in V, right, and then you say that I'm going to copy that state like this, V tensor V, right? So what is this physically? Does it mean that you have somehow cloned the state, that you have 2 electrons and you somehow know that they're exactly the same state? That may or may not be physically possible. Mathematically, in our mathematical model, of course, you could just say, okay, I have one system, V. I have another system, which is going to be in the same vector space, V, a copy of V. So there's an intrinsic identification between them somehow. And then I'm just going to consider states of the form V tensor V. So you could build these states in the mathematical model, no problem. Okay, but what I'm saying is that when you have a certain type of particle, you have more than one of them, and if they are indistinguishable, okay, the question is, what do you mean by that indistinguishability? What you mean is that in the mathematical model, they should be represented by a state in the tensor product, which is invariant under the switching representation. But what does it mean to be invariant? it means that it should be physically indistinguishable, which means it should have the same phase. It should differ at most by a phase. That's how those are the axioms of quantum mechanics, after all, right? So if you have a pair of indistinguishable particles, they must be, they cannot be in any other state than in one of these two subspaces. They cannot be in a linear combination of these. That's what I'm trying to say.
Yeah, that makes sense.
Okay. Okay, so the question really is, there are two possible mathematical models to use for indistinguishable particles. These are the two. And the question is, which are we supposed to use? Okay, so you could think that this is an additional axiom which has to do with the notion of identical, right? What does it mean to have multiple identical particles? It means that we have to change our mathematical model. It's not just the tensor product, because the tensor product has this additional feature of being ordered, and the particles are not ordered. Okay, so I've said it a few times, and those are all I've gave all the available explanations, one after the other. Okay, and it could very well have been that maybe only one of these is used. Maybe the symmetric power is the most natural one to consider. Okay, so let me continue with this development. So for more than one particle, for more than two, for multiple identical particles, we have the same problem. Particles. Let's say we have, for n identical particles, oops. We should find subspaces. We should use subspaces of V tensor V n times which are which have the property that if we take an element in Sn, which is the symmetric group, the permutation group on n elements, that that this should be just a constant times this. So in other words, it should be yeah, we should consider a subspace which doesn't change the physical state. So an example of this is so there's two. So the corresponding subspaces to the two that I mentioned above, there's analogous subspaces like this. The first one is SNV, or sometimes called SymNV. We've seen this before. So these are the +1 eigenspace. And you can build things in this subspace by just, again, averaging over the action of the group. So what you could do is take a state in this fictitious, ordered, tensor product, and we could apply. We could average over Sn. What we could do is just take a sum for all permutations, and what we do is we just permute the indices. Okay, and if you wanted to make it an average, you could divide by n factorial the size of Sn, but it's not necessary. Okay, so then this thing will be sent to itself by any permutation in Sn. Okay, so those are the symmetric tensors, and that's where n-particle boson states live. This is where bosons live here. And then the other one is called wedge NV. And these are called the, this is called the skew symmetric tensors. Or, yeah. And these are the ones which satisfy that if we permute it, we get a sign which is -1 to the sign of the permutation. So the sign of a permutation, okay, the way you should think of it is that it's a group homomorphism from Sn to the Z mod 2Z plus or minus 1 group. Okay, and it takes a certain permutation to -1 to the number of switches. So if you express this as a product of transpositions, which just switch I and J, then the number of these transpositions tells you what the sign of the permutation is. So for example, the permutation 1, 2, which is the one that we used to switch the first and the second particle, right? This has sign -1. Whereas, for example, if I do this permutation, then you could write this as 2 and 3, and then 2 and 1. So this is 2, 3, and then 1, 2. And so this would have sign +1. Okay, and so you could actually think of this thing, just because we've been studying this for such a long time, you could actually think of this as a representation of Sn, and you could think of it as a one-dimensional representation, right? Because every group element is being taken to a 1-by-1 matrix, which just happens to be plus or minus 1. So you could think that the symmetric group has a non-trivial one-dimensional representation, which is called the sign representation. And there's a theorem which I can't prove in this class, which says that the symmetric group has only 2 one-dimensional representations. This one and the trivial one. So there's a theorem that Sn has only the trivial, which is just +1 matrix, and the sign one-dimensional representations. Okay, and this this thing here, this sign is exactly that. So it's because of this fact that the symmetric group has two representations, the trivial and the non-trivial one, that makes the difference between the bosons and the fermions. So so the trivial representation gives us bosons, and the non-trivial sign representation gives us fermions. Okay, so I just want to pause there, just because I know this is kind of bizarre type of idea, but any questions about this?
So, I mean, we can't actually tell the phase, right? Because it's not physical. So the way we would distinguish fermions from bosons the dimension of their state space.
Well, okay. So the question is a good one. It's like you know, how do we know if a given type of particle behaves as a boson or a fermion? Right? How are we supposed to know? Are we supposed to switch it and measure its phase? No. You're right about that. So it's really about I mean, it's true that one of the consequences is going to be a difference of dimension of S2V versus wedge 2V. But there are many other consequences. So you can take your pick. There's plenty of consequences. There's two possibilities, right? So what we're going to do is see what those consequences are. Okay. So for example, okay. This is the example that the physicists would never give, but it's a correct example. So just to emphasize, so let's say that you had a particle which had a state in a one-dimensional vector space. I mean, that seems a bit strange, but every particle has a state, and that state is itself a one-dimensional. It generates a one-dimensional vector space. So every particle is in a one-dimensional Hilbert space. So let's say that V has dimension 1, right? Then, so it's just isomorphic to C, let's say. So then S2V, what would this be? It would be generated by, let's say, E tensor E, where E is a basis for V. So it has a one basis vector, and so it's also has dimension 1. And SNV is generated by E tensor E, right? And so this is also dimension 1. So if you have a particle in a state, and you have the capability of having identical such particles in this same state space, same Hilbert space, right? And if they're completely identical, then one possibility is that they're symmetric, they're bosons. And what this means is that no matter how many identical bosons you wish to have, there is room for them in this mathematical model. If you want n bosons identical in this one-dimensional quantum state space, that's possible because SNV is a non-trivial vector space and it has states in it. So there are bosons of this type, n in number. Okay, On the other hand, if we look at wedge 2v, well, remember how wedge 2v, it would be generated by EI tensor EJ minus EJ tensor EI for EI a basis. Okay, but there's only one basis element, and so we get E tensor E minus E tensor E, and this is 0. So this has dimension 0. It's a 0-dimensional vector space, and it is not a Hilbert space for any system. So this means that we cannot have fermions identical. We cannot have a pair. We cannot have a fermionic pair if the dimension of the state space is equal to 1. So in other words, this is a kind of mathematical way of saying you cannot have two fermions in the same state. Okay, whereas you can have n bosons in the same state. So whatever that state is, right? For example, if we had let's say we had a two-dimensional state space, our favorite quantum system, the switch, right? So if, for example, another example, suppose that V is C2, this quantum switch, the qubit. Then let's say we have n identical qubits. Okay, now, at Google, when they have their however many 32 qubits or something, they're not identical. I mean, they're actually laid out on a chip. They're actually, they have different positions. You can look at them and see that they're in different positions. So they're not identical. But if you had n identical qubits, then you have two possibilities. You could take NV, or you could have wedge NV. So how does this series behave? So if I take, you have V has dimension 2. If I take S2V, this would be basically symmetric. This would be, let's see, what's the easiest way to count them? You could take, this would be generated by EI tensor EI, or EI tensor EJ plus EJ tensor EI. So it's really n choose 2 plus n, which is n, this is n plus 1 over 2. Or in this case, since V is two-dimensional, this would be 3. And if you take S3V, this would be 4, and so on. Okay, I'm just counting symmetric combinations of the basis elements. So if you wanted 3 identical qubits, that means that your state space would actually be 4-dimensional if the qubits were bosons. So if the qubits were bosons, then 3 qubits have a 4-dimensional state space. Okay, and n has n plus 1 dimensions. Okay, and so the people who are trying to build qubits, they definitely don't want them to be identical, right? You want to be able to do a computation and then to make a measurement on one of them, not on the entire joint state, and so they would not be happy with only they do all this work and they do 32 qubits and then they end up with a 33-dimensional state space. That would not be sufficient for them. They need to do these amazing calculations which require a 2 to the n if you compare this with V tensor n, this would be 2 to the n dimensional. Okay, that's what they're exploiting. That's what you want for quantum computers. Okay, but then if they were fermions, then they would really be killed, because if we look at the dimension of V, that would be dimension 2. If you look at wedge 2V, that would be generated by n choose 2 only. E1 tensor E2 minus E2 tensor E1. That's it. There's only one generator, so it has dimension 1. And then wedge 3V, well, there's no more room. It's 0 dimensional, and it just dies after that point. So that means that if you had, for a state space that has only 2 dimensions, right? If it was fermionic, then you cannot have multi-particle states beyond two states. You cannot have 3-particle qubit fermions. It does not exist. So 3-particle fermion qubits. So sorry, I hope that it's clear. I don't want to kind of write a theorem or anything to this effect, but this is what happens in the case where V is 2-dimensional. Okay. Now, okay, I just want to say a few, just one remark, just not to give anyone the wrong idea. So inside V tensor n, there are many more irreducible representations of Sn. V tensor n, it actually decomposes as a sum of irreducible representations. One of them is SNV. One of them is wedge NV. But there's a whole bunch of stuff in between. And these are indexed by so-called Jordan block. Sorry, what do they call them? They're indexed by what are those things called? Jordan blocks, I guess. So there's you should learn about this in a course on group theory. You take some blocks and you make some Lego patterns like this. So there's the one that is completely vertical, there's the one that's completely horizontal, but then there's other things in between which have a mixture. And so there are other irreducible representations, but they are not they're not used in physics. The particles, identical particles, do not behave under these representations. Yeah. Okay. And right. Okay. So all right. So let's go back to the hydrogen atom with this in mind. Is there a question?
So it's not exactly related to the material. I was just wondering if we have a quiz today.
Oh, no, there's no quiz today.
Okay.
Oh, because you want, because normally we would break at this time. Okay, let's break and come back at 3:15, and I'll explain the application of this to the hydrogen atom. Okay, see you later. Okay, so let me just share this for a second. Yeah, here we see the representation theory of the symmetric group. I don't know if that's visible. The symmetric group has order n factorial, and the conjugacy classes are labeled by partitions of n. Okay. The number of inequivalent irreducible representations over C is equal to the number of partitions of n. And so you end up with these Young diagrams. That's the word I was looking for. Where's the Young diagrams? Young diagrams, they look like this. You could either draw it. So this is a partition 1, 2, 3, 4, 5 plus 4 plus 1. So it's a partition of 10, just drawn as a bunch of boxes, 5 plus 4 plus 1. Okay. And you can see here the some of the representations. So this trivial representation of Sn is a partition of n, which is just n. It's not partitioned. So you draw that as a single row of length n. The sign representation, it also has dimension 1, but it corresponds to the partition where it's 1 plus 1 plus 1. So the two extreme partitions are the trivial and the sign representations, and they both have the same dimension. And the standard representation V, what they mean by standard representation is that you take, so the standard representation just means that if you take an n-dimensional space with basis, n basis elements, right, then you can permute the basis. And that will give you a representation of Sn on C to the n, right? But so let me go back to my page. This is maybe just to tell you a little bit about these things. So if we have Sn, this obviously acts on C to the n, and it takes E1.
Sorry, I think it hasn't loaded yet.
Oh, thank you. Okay, yeah. So Sn can act on C to the n, and it just takes e to the I, ei, the ith basis element, to E sigma of I. Right? And what you notice is that there's a very special vector which is invariant under this. Inside here, note that E1 plus E2 plus En is invariant. And so there is a one-dimensional ray generated by 1, 1, 1, which is sent to itself. It's an irreducible trivial sub-representation. So what you need to do is take the orthogonal complement of that. The orthogonal complement of the 1, 1, 1 subspace. This is the standard representation. And it corresponds to the Young diagram where you have n minus 1 boxes and then 1 box left out. Okay, so all I'm trying to say is that when you take your n boxes and you reshuffle them into various different shapes for the different partitions of the number n, each of those corresponds to a single irreducible representation of Sn, and only two of these possibilities are used by multiple particles in physics, the extreme ones. Okay. And it's because those are the only two one-dimensional representations. The other ones have higher dimension representation. Okay. Okay, so what impact does this have for, let's say, oh, right, sorry, so there's something important that I forgot to say. So the spin statistics theorem is a statement which, for elementary quantum mechanics, we could treat it as an axiom, but it can be proven in quantum field theory, or at least in relativistic quantum mechanics. Actually, I think there should be an elementary proof in usual quantum mechanics, but it would take us a little bit too long to get to that. And that is to say that that the spin, so there's a relationship between SU2 representations and statistics. And this SU2 here, this is really viewed as part of the Poincare group of symmetries of our universe. So this is SU2 inside P. In the assignment, I describe what P is. The universe appears to have a group of symmetries which involves rotations in three-dimensional space, translations in three-dimensional space, and also translations in time. And as well, there's these Lorentz boosts, Lorentz transformations. So there's a group which contains SO3 and contains SU2, which acts on physical reality. Okay, and every particle behaves under a representation of this group. And the theorem is that the statistics of the particle, the statistics of multiple identical particles, is related to which representations of the Poincare group it has. And that relationship is that if it's integer spin, then it's a boson. And if it's half integer spin, it's a fermion. So so this means that matter particles, electrons, protons, neutrons, quarks, you name it, these are all half integer spin 1/2. And these are fermions. And the force particles, photon, photon, gluon, WZ, etc. These are spin, Higgs, how could I forget the Higgs? Spin 0 or 1, and these are bosons. Okay, and the dimensions, remember that integer spin, these have odd dimension for SO3, and these have even dimension for SU2. Okay, so I don't want my statement to be confusing. The fact that the qubit is a two-state system, a two-dimensional state space, the fact that it has two classical states, up and down, spin up and spin down. Sorry, let me scratch that. Let me start again. So just because you have a quantum system that has dimension 2, and just because you have an SU2 acting on that quantum system, it says nothing about the statistics. The SU2 that I'm talking about is really the SU2 of the rotations of three-dimensional space. So the idea is that if you have a particle or a system that behaves under rotations as a spin 1/2 particle, then it will behave as a fermion when we start to accumulate more than one of these particles. So anyway, that's the spin statistics theorem. So now, any questions about this? The reason we need this is because when we're analyzing the hydrogen atom, the particle that we're talking about is actually an electron, and that is of spin 1/2, and that means that it has, so the state space of an electron is L2 R3 with complex values, tensor V1/2. This is a two-dimensional Hilbert space, which behaves as the standard representation of SU2. So, right. And so, well, I mean, the fact that it has this V. So let's just focus on the component of the state, which is in the let's just focus on the spin state. This means that we can have one electron or two electrons, but not three in this three identical electrons, just because wedge 3 V1/2 is 0. So we have basically, just to draw a picture, if V1/2 is generated by spin up, let me call it spin up and spin down, then a two-particle state would have to be, well, it would be up tensored down, or in other words, minus down tensored up. This is the only possible multi-particle state of an electron. So this is usually abbreviated like this. Okay, so let's take let's grab a let me see, where's my diagram? No, it's up here somewhere. Okay, so let's suppose that we want to put 3 electrons into this atom. This is, what is this element? It's the one right after helium. It's lithium. We're going to put 3 electrons into this infinite dimensional state space, but really, it's really L2 R3C tensored with C2, right? The two-dimensional space V1/2. So we want to consider wedge 3 of this space. Let me call this big space V. So my 3 electron state are exactly in here because electrons are they are fermions. And so we need to look inside wedge 3V. Okay, that's where my 3 electron states are. Now, this L2, this might be fearsome. It's an infinite dimensional Hilbert space. But the diagram just above is a decomposition of that L2 R3, right? That's what this diagram really is, right? We used various operators and took their we decomposed L2 into eigenstates for that operator. And what we found is that according to the eigenvalues of the energy Hamiltonian operator, we have a one-dimensional part of this L2 sitting at the lowest energy. And then we have another one-dimensional, and then we have these this three-dimensional representation of SO3. And then this is repeated, and then I have a five-dimensional representation of SO3, right? So this is how we decompose L2, and we don't need to worry about this whole L2 because we're not going to put in electrons of huge energy. We're going to assume that they are filling up the lowest energy states, the easiest ones to fill. So if I'm going to put 3 electrons, well, okay, so the first one is going to go exactly in this state. So I need to take this diagram and I need to tensor this by V1/2. And that means that each one of these boxes actually represents not a one-dimensional space, but a two-dimensional space, because I'm tensoring it with the V1/2. So each box represents a 2D subspace of V, of the full tensor product. Okay, and okay, and so what should we do? So we're going to assume that that when we wedge these, this is just called the wedge product. So when we wedge V with itself 3 times, what could happen? Well, you know, we can just consider the first few energy levels. So we could just consider, let's say, 1s direct sum, 2s direct sum, 2p, 2p, 2p. Let me just write it this way just to be as explicit as possible. And this will continue on. Okay, this is L2. Okay, and then I'm going to tensor this L2 tensor V1/2 is going to be just every one of these is going to be tensored by this. And it'll continue. So this has dimension, let me just draw the dimensions below. This has dimension 2, this has dimension 2. This part here has dimension 1 plus 1 plus 1, dimension 3. It's a 3-dimensional representation of SO3. And then I'm tensoring it by 2, so that's 3 times 2, and this would be 6-dimensional. Okay, and then I need to, so this is a description of the entire vector space V, and then I need to look at wedge 3V. And if I look at the first few terms that we'll get, so what would be the lowest energy subspaces of this wedge 3V? Well, one possibility is to take wedge 2 of this 2-dimensional space, 1s tensor V1/2. Okay, that's 2 electrons in the lowest energy state. And where's the third electron going to be? So let's see. Sorry, let me do wedge 2v first, just to. So this will have wedge 2 of 1s tensor v 1/2 plus more stuff. And that's usually what people mean when they take this box and put 2 electrons into that orbital. So that would be, yeah, they would consider that orbital to be filled, the 1s orbital. And then we'll put in another electron. The next one will go in here. And yeah, sorry. So I kind of went a little bit too quickly. So I guess I'm going to break up the computation into 2 pieces. So these states and these states, they are distinguishable. They have different energy. Okay. So when we put 2 electrons, a 2 electron kind of combined state, combined system into this atom, they're going to fill the 1s orbital, and the state will be. So maybe let me simplify this a bit. So if we put 2 electrons in, we'll get wedge 2 of this 1s tensor v 1/2. And this is, I guess, usually written as I guess 1s2. The next electron, sorry, I wanted to go into a different. Yeah, okay, that's fine. So the next electron goes in 2s tensor v 1/2. So so that would look kind of like this. And the so this would be in, yeah, sorry, I was going a little bit too quickly, but I guess the point is that we would have the complete state would be wedge 2 1s tensor v 1/2 tensored with 2s tensor v 1/2. This is where the electron state would reside. We have a pair of particles at one energy level, and then another particle at the next energy level. So the yeah, and then if we wanted to continue, and this is, I don't think I had time to get to this last time. You can see that as you start filling, as you start adding more electrons, right, what happens is that you fill first the 1s, So this is one electron. This is a second electron. Then the 1s is filled with a pair of indistinguishable electrons. And then when you, the next energy level that is available to fill is 2s. That's, again, a one-dimensional space inside L2, tensored by V1/2, always tensored by V1/2. So that means that there's the availability of 2 electrons in the next energy level. So that's lithium and beryllium. But the point is that after 2, you cannot place more than 2 electrons in that one-dimensional subspace of L2 because they are fermions. And there is no wedge 3 of the 1s. There is no wedge 3 of 2s. So once we do wedge 2 of 1s, we're done with 1s. And once we do wedge 2 of 2s, we're done with that. That's the reason why there's only hydrogen and helium, lithium and beryllium. Okay. And then the 1s and 2s are filled. So if they were not fermions, we would be able to continue to place electrons into the 1s. We could take higher and higher symmetric powers of 1s, and we would get bigger and bigger spaces, and we would be able to put the electrons into the 1s orbital. But we can't do that because of that fact that the 1s essentially represents a two-dimensional state space, and wedge 2 is the highest power you could have for skew symmetric tensors. So after 1s and 2s are filled, then the next level is the 2p, and the 2p is not a one-dimensional subspace of L2, but it's a three-dimensional representation of SO3. And so that means that we get 3 tensor 2, which is 6. So we end up with 6 possibilities, B, C, N, O, F, and NE. These 6 additional electrons, they are all filling in the 2p orbital, which represents three-dimensional tensor V1/2. Okay, and then once we have put 6 electrons in, that means that we've reached wedge 6 of 2p. 2p has dimension 3, right? So maybe let me switch back if I can. It's a bit awkward. So if we want to fill, suppose that if we fill 2 electrons in 1s and 2 electrons in 2s, so this would be a state in wedge 2.
We don't see it.
Oh, yeah, of course. Inside, so if we fill 2 electrons in 1s, that would be a point, that would be a vector in wedge 2 1s tensor V1/2, which has 1 dimension. And then this is wedge 2 1s 2s tensor V1/2. But now if we want to put an electron in 1p, or sorry, 2p, that's the way they're labeled up here. Right? This is a three-dimensional subspace of L2 tensored by V1/2. So we get 2p tensor V1/2. And the question is, how many electrons can we put in here? So we can put 1, we can put 2, and so on, all the way up to 6 2p tensor V1/2. Right? This has dimension 1. This has dimension 3 times 2. So this has dimension 6. This has dimension 6 choose 2. 6 times 5 over 2. So that's 15. And all the way up to here, which is 1. So if you calculate these, you'll see that it runs out after this. Wedge, you cannot put more than 6. Wedge 7 is 0. So there's a possibility now of adding 6 electrons into the 2p orbital, and that's usually written this way: 3, 4, 5, 6. And in the periodic table, those are exactly this is exactly the reason for this set of elements up here. These. And once the 2p is over, then the next level in our classification is 3s. So it's again a one-dimensional representation, back to one dimension, and we have 2 electrons to fill there. And above 3s is 3p. So these are the 6 electrons to fill 3p. And we continue with that. And the interesting thing that happens is that after 4s, there is a 5-dimensional representation. It's d. Okay, and that gives us 10 electrons. So we can fill 10 states here. And after wedge 10 of 3D tensor V1/2, I'm done with 3D. It's filled. And I go on now to 4P, which has the same dimension as 3P, right? And you continue this way until you reach 5P. After 5P, which is right here, 5P, once it's filled, we go to, how does it go? No, after 4P, we get, so then we get 6S, and then we get this 4F, the last one. And the 4F is not a 5-dimensional representation, but it's a 7-dimensional representation of SO3. And that's why we have 14 possible electrons to add in. Okay, so this is exactly the reason. So the representations of SO3, coupled with the fact that the electron has spin 1/2 and therefore has a 2-dimensional internal spin state, is the explanation for the magic numbers of the periodic table. They're always two times the dimension of the SO3 representations, which are always odd numbers. So you always get 2 times an odd number. Okay, and so that's a kind of really simple, once you know the representation theory of SO3 and the fact that the exterior algebra or the fermionic nature of electrons, it gives a complete explanation for the shape of the periodic table. So any questions about this this argument?
I have a small question.
Yeah.
Can't you is there like an upper cap? Can't you go to infinity and just have like infinite periodic table with like a bunch of?
Yes, absolutely.
Really?
Yes, but the problem is that what breaks down is not the electron. What breaks down is the nucleus. See, everything that we've done so far, it depends on the fact that the nucleus can be built. This tiny, tiny speck at the middle, which has positive charge, which has to increase. The more electrons you put, the more charge you need to put in the nucleus. But I mean, you try to put a bunch of protons together and see how well that's going to work out. You need to glue them together with a force that is stronger than electromagnetism because they're all positively charged. And the only force that's available is the weak nuclear force. I mean, it's called weak, but it's not weak. And the only way you can do that is by putting neutrons in. And so then you have this huge ball of neutrons gluing together these protons who don't want to stay together. And that's the problem, is that after you put too many protons together, it becomes unstable. And so the decay, the time that it lasts before it breaks apart just gets bigger and bigger. And so, of course, in theory, if you could go in there and you could, make more protons stick together, then you could build huge atoms without limit. That's the problem. Gina?
I just have a really brief question.
Yeah.
So earlier we were talking about, tensoring the 1s v1/2, 2s v1/2, all of that with the wedge. So when we put the wedge, do we tensor or do we direct sum with
Okay, so yeah, good question. So let me go back. You need to be a little bit careful. That's the reason why I was trying to avoid discussing this in too much detail. When you take a wedge product of u plus v, suppose you were doing something simple like this,
Are we
where
still?
you, oh yeah, of course.
Thanks.
Yeah, thank you for telling me. So when you take a direct sum and you take wedge 2 of it, okay, there is a nice law for this. So you could take, so this turns out to be wedge, and you can do this with basis. The easiest way to figure this out is just by using a basis. So this turns out to be equivalent to wedge 2u, wedge 2v. But there's also the possibility that you could take, let's say that this had like basis E1 up to En for u and F1 up to Fm for v. So this would be EI wedge EJ. These would be the skew symmetric elements that are built only from u. These would be the skew symmetric states, the fermionic states built only from v. And this wedge product just means E1 tensor E2 minus E2 tensor E1. Some people include a factor like divided by 2, but there's no need for that for the purposes of this talk. Okay, and then there's the ones that you could do like this, EI Fj minus Fj EI, the ones that are take one state from U and one state from V and then skew symmetrize them. Okay, so that's the third possibility, and that is isomorphic to U tensor V. So it's kind of funny that U tensor V shows up even though I want it to be skew symmetric. So you need to be careful when you write this. You need to remember that this U tensor V is sitting inside here, and so the elements should not be thought of as being just simple tensor products, but rather skew symmetrized tensor products. Okay, but this decomposition is correct, and this you can even count the dimensions. Like if this has dimension m and this, sorry, if this has dimension n and this has dimension m, this would be n choose 2, this would be m choose 2, and this would be m times n. And it turns out that this m plus n choose 2 is actually the sum of these three. So in general, the formula for computing an exterior power of like wedge 3 of a sum W, it is kind of complicated. So I don't want to go into that. But at least in this case, for two particles, it's really simple like this. Okay. Oh, wow. Okay, so there's no time. So what can I, oh, right. Okay, so let me just say one other loose end. And that was this, this issue of the selection rules. Okay, so what we saw was that we basically have these states. So for the angular momentum, there was L equals 0, L equals 1, L equals 2. And for each one of the values of L, we had multiple copies of that representation of SU2, of SO3, sorry. This is the dimension 1 representation, the dimension 3 representation, the dimension 5, or in other words, S, P, D, and so on. But for each one of them, depending on the radial eigenvalue for the Laplacian, for that radial Laplacian, we got a sequence, 1 over n squared energies, okay? So there were these energy levels, 1s, 2s, 3s, and then they accumulate like that. And then we had 2p, 3p, and so on, and then 3d. This is how they were arranged, okay, based on the solution to that ODE. And what I said was that if you were in a particular state, and if you wanted to decay or absorb, it doesn't matter, you could not, so there's a forbidden move. So moving within one column is forbidden, and moving from one column across one column to two across is also forbidden. The only thing that is possible is going from one column to an adjacent column. That's all. Only adjacent decay or absorption or emission. Okay, and the reason for this, if you remember what I was saying, is that when the photon comes in and intersects the electron, this is before, and then after. So this electron is in some state, right? And then at the end, you have only an electron, but it might be in some other state, right? So this is maybe 1, 2, 3, and so maybe before we had a photon and an electron in a certain state, and then after we have only an electron but in a higher state. Okay, and so there must be, okay. And the point is that all of this is happening in the lab, and I can rotate the lab. I can rotate it before, I can rotate it after, and the electron and the photon do not care. Okay, so that means that as a representation of SO3, we have V1 tensor V1 half before, because we have the photon and the electron, and after we have the electron. Okay, but the electron is in a certain state. So actually the electron is not in V1 half, but it's in VL tensor V1 half for one of my VL states, one of my angular momentum states. This is a subspace of L2 R3, right? And this is the internal spin. So the electron in our system is I'm assuming that it's in a particular angular momentum state. And at the end, it's got to be somewhere. So at the end, well, what can it be? Well, if we tensor these together, this actually decomposes as VL minus 1 plus VL plus VL plus 1, all tensored by V1 half. So this is using the Clebsch-Gordon. So, before it was in a certain representation, which was easy to determine because we had the photon and the electron. They were separate, and we know the photon is it's a spin 1 particle, so it's in V1, and the electron is in our atom. So we have this. All we need to do to figure out what the outcome could be is to tensor these together and decompose, and we see that it could go either to the previous column, to the same column, or the next column. Okay, and what I'm saying is that these two are the only possibilities. And this one is forbidden for some reason. Why? Well, okay, I just want to point out that there's a whole bunch of other possible spin states that are also forbidden because of the Clebsch-Gordon decomposition, right? We already excluded the possibility of going to L minus 2 because it's not contained inside this representation. Okay, so we managed to exclude a lot of stuff by using the representation of the group. And it turns out that in order to exclude this, we need to use another group that happens to act here. So there's a further group. It's a Z mod 2Z. It's a discrete group or a finite group, which takes X, Y, Z and maps it to minus X, minus Y, minus Z. Okay, this, the potential, the entire system is invariant under this thing, which is called the parity reversal. Okay, and let me let me just investigate here what's happening. So parity acts so parity acts on the usual three-dimensional representation. What's the usual three-dimensional representation of SO3? It's just R3. It's the most obvious representation. So when we do a parity transformation, it acts by -1. It has eigenvalue -1 on V1. Okay, and this okay, and then it will act on VL as well. And it depends on whether VL, it depends on whether the spin, it depends on whether the value of L is even or odd. If L was 1, then it would act by -1 on here. If it was 2, then, so in other words, if it was, let's see, how to explain this. VL yeah, right. So let's just take a look at this equation. V1 tensor VL is VL minus 1 plus VL plus VL plus 1. Okay, so if we act by parity, right, then there are two possibilities. If L is even, let me put odd first. If L is odd, then parity acts by -1 tensor -1, which is +1. But if we look at the right-hand side, parity will also act on the right-hand side. How does it act here? Well, I assumed that L was odd, and therefore that parity should act by -1 on it. And if L is odd, then these two are even. And it would act by +1 and +1 here. So you see that this simple reflection acts on the left-hand side by +1. And on the right-hand side, it acts by +1 or by -1. So this must not be present. This violates parity symmetry. So, so this is excluded since P is a symmetry of the system. If you look at, for example, the Hamiltonian is independent of reflection. It depends only on the radius. On the other hand, let's do the analysis in the other case. If L is even, the opposite is true. P will act by -1 tensor +1, which will be -1. This one will be +1, these will be -1, and the same one will be excluded. So the same argument holds. So if L is even, the same summand is excluded. Okay, this is the kind of group theoretic explanation for the selection rule. So this happens a lot. In fact, this is often the reason. This is often the way that symmetries of nature are discovered. The way they're usually discovered is that you say, okay, I'm going to take two particles, and I know what the particles are, so I know what their representations are for the symmetry groups of nature, because I've studied these particles for decades, right? A proton and a proton, I know what they are. Then I smash them together as hard as I possibly can, and I look at what comes out. And all those things, they must be the summands of the tensor product. They must be contained in the summands of the tensor product, roughly speaking, okay? And if we notice that one of the summands just is not showing up, that there's a missing summand, there's a missing type of particle in the result, that's usually because there's a selection rule. And the selection rule must come from an additional symmetry, which would be violated if that summand were allowed to exist. Okay, and so it constrains the interaction. So in other words, the way that a photon interacts with an electron prevents the possibility of the electron staying within the same angular momentum state. It must go to a different angular momentum state. And that angular momentum state cannot jump 2 levels of spin. It can only go up by 1 or down by 1. Okay, and it is basically a law of nature that governs the interaction between a photon and an electron. The interaction does not allow, a transfer from L equals 1 to itself. So it's really just this parity argument which explains the selection rule. There are more complicated ones, like when you're dealing with crystals, for example. Crystals have very much more sophisticated 3-dimensional discrete groups of symmetries, and so you can often exclude certain behaviors of a crystal by imposing these symmetries and throwing out certain representations, and getting kind of these remarkable facts about why crystals don't behave in ways that you might have originally expected. Yeah, hopefully that gives you a flavor for that. So anyway, that ends discussion of the atom and so on. We're going to go to Wigner's classification next week, and do the Feynman diagrams. Any questions about this this stuff? This argument is a very rough argument, right? We're not actually studying the exact kind of dynamical behavior of the system as the photon comes in and modifies the Hamiltonian, and it's obviously a very complicated system, but all we're doing is using a very rough symmetry argument, and that's enough to kill certain transitions. Which, I mean, interestingly, that means that you can look at a spectroscope, you can look at the spectral emission lines for hydrogen, and you can deduce that you can deduce, for example, that the photon has spin 1. Because you can see that there's all these other impossible emissions are excluded. They're not present. But anyway, yeah, it's not, it requires a lot of precision because these levels are almost the same. So for example, like the decay from here to here, which is not seen in a spectral line, but this decay would be seen. So what I'm saying is that this decay energy, this frequency of emission is very slightly different from this one. And you will see this one and not this one. And so you could conclude that, that it must be of spin 1 since this is excluded.